Welcome to my talk about Xenpwn, breaking paravirtualized devices. And before I start with the actual content, and while all the people are searching for seats, I'll start with a short introduction about myself. So my name is Felix Wilhelm. I'm a security researcher at ENW Research, and I'm mainly interested in application and virtualization security. So in the recent years, I mostly concentrated on security appliances on the one hand side. So we did some research on the FireEye malware protection system, as well as just last week at Troopers, I did publish some research about the Palo Alto next generation firewall. And besides that, mostly working on hypervisors, which will be the content of this talk. You can also find me on Twitter, so please follow me. Okay, so to start with the actual agenda, what's the topic of today's talk? I will mainly talk about paravirtualized devices or the security of paravirtualized devices. And so the first part of the talk will be a short introduction. What is device virtualization and what are paravirtualized devices in contrast to normal device emulation? Then we talk a bit about a certain vulnerability type, the double fetch vulnerabilities. And I'll present my tool, Xenpwn, which is designed to automatically identify these double fetch vulnerabilities in paravirtualized device communication. After that, I shortly go through the interesting results I discovered using this tool, and then the last and the main part of the talk will be a case study where I walk through a full hypervisor breakout exploit using one of the bugs I discovered using Xenpwn. So let's start with device virtualization. Basically, if you have a virtual system, you need access to virtual devices. And these devices can be like disk or network or serial devices and everything you can imagine. And traditionally, everyone used device emulation for that. So the core idea of device emulation is simply emulate old and well-supported hardware devices. So your guest operating system probably already has a driver built in. You don't need any special drivers, and you can just install your operating system using the standard ways in your virtual machine, and it will probably just work. So just like the security risks of device emulation are quite well understood. We even had like the talk yesterday about fuzzing the QEMU device emulation. And there's a lot of research out there. So these are like just like a couple of examples. For example, Tavis Amandi released IO fuzz, which basically did fuzzing of port and memory mapped IO. And at that time, when he released that tool, you could crash like every virtualization software in existence just by booting that live CD and letting it run for like half an hour or something. And last year, we had like the Venom bug, which was a floppy disk controller bug. So it was part of the QEMU code, and you could use that to break out. So in summary, like device emulation is quite hard to implement securely and correctly, and you will find a lot of bugs in that. So why I'm talking about paravirtualized devices? Like emulated devices are kind of slow or extremely slow. I mean, they emulate like devices from the 90s most of the time. So you have no advanced features, and like emulating memory mapped I/O and port I/O in a virtualized environment triggers a lot of VM exit. You don't have a lot of bandwidth. So overall, it's really slow for like the whole performance of the system. So every major hypervisor decided, yeah, we don't want to rely on emulated devices completely. We also want to have like special kind of device drivers that are optimized to be used in virtualized system. And the solution is like paravirtualized devices. So these are like devices that know they don't talk to actual hardware, but instead are optimized for use in virtualization. And it's basically a specialized device driver that you can use. And if this driver isn't available to a virtual system because it's not installed or something, you can still fall back to emulated devices. So that's why you always have like a QEMU running on under KVM or Xen or something. But it should only be used as a fallback mechanism. And if you actually look at like a running system running under Xen or Hyper-V or something, you will see they're actually relying on these paravirtualized devices. So how is this stuff actually implemented? It's always, or at least all the architectures I looked at, is always implemented as a split driver model, and that's where it starts to be interesting. So I have a front end that runs in the guest system, and the front end basically just looks like a normal device driver. So on Linux, it's just like a normal kernel module that looks to the rest of the operating system just like a normal device driver talking to some kind of, I don't know, disk device or PCI device. And then you have a backend, and the backend runs in the management domain or on the host system. So on Xen, it's the management domain. On KVM, it would be the host system. And while the terminology differs between the hypervisors, so on Hyper-V this is called like virtualization service client and virtualization service provider, it's more or less the same implementation for all of them. On KVM it's called virt.io. When you look how they are actually implemented, and this is like something that's interesting if you want to target them, they are all implemented on top of shared memory. Why on shared memory? Because it's really great for performance. So you just like exchange messages over your main memory. So it's really fast in comparison to like a network stack or something. It's really easy to implement, especially if you already have like a hypervisor running. Then like sharing a physical memory page between different execution contexts is like, it's one of the main purposes you probably use a hypervisor for. And you can do like advanced stuff like zero copy algorithms. So like the network traffic generated in your guest virtual machine can be directly passed into like the DMA memory region of your network card, for example. So this all makes it like the most performant way to do these paravirtualized devices. And of course, if you just have like a shared memory page mapped into your VM and your management domain, you can't directly like use this for message exchanging. So everyone implements basically ring buffers on top of this shared memory regions. So you have just like the classical ring buffer algorithm to exchange or to emulate some kind of message passing. And of course, on top of that, you have more complex protocols. So it's basically like a network protocol stack. So you have like shared memory at the bottom, then you have like the ring buffers on top of that. And the messages exchanged using these ring buffers are like really device specific messages. So every front end and back end driver has potentially a completely different kind of protocol. These protocols are also kind of complex most of the time, which of course these are like, this is the attack surface we want to look at. You can like target these protocols like you would do target normal network protocols. And so like an implementation detail is that these shared memory mappings, they can be like created on demand. If you want to like exchange a lot of data with like a single package, or they're just created, they are just constant, so they will be created during boot up, and then the devices communicate with each other over these constant shared memory mappings. So why should we look at these paravirtualized devices, or why should we be interested in them? The idea is that you have a backend and that runs in a privileged context, so on the host system or in the management domain. So all the communication going on between the front end and the back end is a trust boundary, and if you can exploit in the back end, you can break out of your virtual environment. It's low-level code, it's parsing, so it's protocol parsing, so there are bugs. There are also some publicly reported vulnerabilities, but interestingly not very much. Like there's a heap-based buffer overflow in the KVM disk backend. It was reported in 2011. And last year, someone from Microsoft actually reported a buffer overflow in the Hyper-V storage backend. And this, I think, is actually the first example of a vulnerability that was internally discovered by Microsoft, but still got credits on Patch Tuesday. So this was one of the first examples for Microsoft actually credited an internal researcher for his work. And it seems to be that these kind of devices are not as scrutinized, so not as many people are looking into them as it is the case for emulated devices. And I think the reason for that is mainly that you have like device and hypervisor specific protocols, so you have to do some kind of source code reading or reverse engineering until you really understand what these devices are doing. And they're harder to fuzz because it's not like simply port I/O or memory mapped I/O. Instead, you have to create these shared memory mappings and put data in there. And So for example, for Xen, if the front end misbehaves, so it sends like messages that don't make any sense, like the complete device will just be killed. So you have to completely reset up and stuff like that. So it's not like, it's not easy to fuzz this stuff very efficiently. I still think they're a very interesting target because nowadays, if you look at the device emulation, most of them is done in user space. So for KVM and Xen, you have the QEMU process. If you look at Hyper-V, you have this VM worker process, and they are all nowadays they're heavily sandboxed. So QEMU is running in a SE Linux container. VM worker process is heavily sandboxed using the whole Windows permission model. On the other hand, all these paravirtualized device backends, at least the ones that are required for high performance, so the network and disk backends, they are often simply implemented in kernel space. So the kernel or the backend module is a kernel module. That's the case for Hyper-V, for KVM, and for Xen. So this means if you find a bug in one of these backends, you have a direct kernel compromise. You don't have to, or you don't require a second like sandbox escape or something like that. You're directly in kernel context of the management domain, which is an instant win for all use cases. So the Xen developers often argue that, yeah, you don't compromise the hypervisor with that, so it's not like a hypervisor compromise, but you compromise the management domain, which in turn like manages all the other virtual machines. So for like practical purposes, this is like a complete compromise of the system. And paravirtualized devices also become more and more important because virtual machines need access to more and faster and different devices. So you have more device types, so you have PCI pass-through, you want to support touch screens in your virtual machine, you have 3D acceleration and stuff like this. And all of this is implemented on top of these paravirtualized device mechanisms. And also, of course, this stuff doesn't get easier because if you compare like the performance of KVM and Xen with each other, the main differences you will see is the performance of these paravirtualized devices. So that's like an area where they really want to optimize because that's the area where they can like get performance advantages in comparison to the other implementations. And then there are some software vendors, or especially Microsoft, that decided to completely remove emulated devices because they are such a popular attack surface. So if you have a Hyper-V Generation 2 VM, which as of now can just be a Windows VM, then there doesn't exist, or there don't exist any emulated devices anymore. So instead you only have paravirtualized devices. So this means if you want to attack devices, you have to attack the paravirtualized ones. So the goal of the whole research I present today was basically find an efficient way, or find a way to efficient vulnerability discovery in paravirtualized devices. So I don't want to like do full manual source code analysis. I especially don't want to do like manual reverse engineering of proprietary hypervisors. So I wanted to have some kind of way that's automated. And it should work against open source software as well as against proprietary software. And the core idea is basically there was no research published that talks about the use of shared memory in paravirtualized devices, which is interesting because there's a certain bug class that only affects shared memory interfaces, and that bug class is called the double fetch vulnerability. So what is a double fetch vulnerability? It's a special type of time of check to time of use bug that affects shared memory. And to define it really simply, it's basically you have a privileged process, and that privileged process fetches 2 times or multiple times from the same memory address, and it performs some kind of validation, but that validation is missed like once. And this is like a generic bug class, and it can introduce a lot of different kind of vulnerabilities. So you can, after that, it more or less allows you to bypass one check. So you can have arbitrary reads, arbitrary writes, you can get buffer overflows, you can get direct instruction pointer control, as we will see later on. And so it's a really interesting bug type. Of course, I'm not the first person talking about double fetch vulnerabilities. So when I published a short teaser blog post, I had like a short history section, but I directly got feedback from Spender, from GR Security, that I missed a couple of guys. So the sources on the right are hopefully like the oldest one, or the first ones I discovered, but if I'm still missing some guys, please don't be angry with me. So I think the term double fetch was first coined by Fermin J. Zerner in 2008 in a blog post to the Microsoft Research blog. But it was just like the terminology double fetch. The bug clause was well known before that. So most of the research was published around 2007, 2008. There was a Usenix paper exploiting concurrency vulnerabilities in system call wrappers from a guy called Robert Watson, where he basically used double fetch to bypass system call filtering. And there was a CCC presentation and a FRAG article, so this classical attacking the core FRAG article actually also talks about these race conditions, and it was written by Twiz and EsgraQ, I hope I pronounced that correctly. And they talk about one Linux bug, which is the first public example of these double fetch vulnerabilities, and that's the Dissent Message Bug. So this is like a simplified version of the shellcode of this bug, and basically what you can see, you have in line 5, you have a call to this getUser function, which copies something out of the user space, and it puts the value into this UCM_len integer variable. And that variable is then used to perform a memory allocation on the heap, so it's like a length field. And later on, they have a second call to this getUser function, which again copies the value from user space into this UCM_len variable, and then uses directly at the length argument for a copy operation. So of course, if an attacker is able to switch the value that is stored at that address between line 5 and line 18, then you have a trivial like overflow vulnerability, and this is trivially exploitable for like a local root escalation. And so this is a simple example for the double fetch vulnerability because you can actually see it in source code, and it's like 2 invocation to this copy from user function. But as we will see later on, that's not what happens in most of these cases. So after this research in 2007, 2008, there wasn't that much published about double fetches until 2013, where there was the paper identifying and exploiting Windows kernel race conditions via memory access patterns by Yoru and Xenpwn. And it's also known as Xenpwn. And the core idea is you have an extended version of Box, so of the Box CPU emulator, and they trace all memory accesses from kernel to user space to look if the kernel accesses like a single memory address multiple times in a row or like in a short time frame. And this is an indication of a double fetch vulnerability. So if they find this, they do manual analysis and start looking at that code path in more details. They used this tool successfully to like find a significant number of Windows bugs. So they had like a lot of local privilege escalation bugs discovered in Windows. They also won a bounty for that, which was well deserved. But nobody really continued working on that topic. So they even released like the Xenpwn source code, so you can use it for your own research. But there wasn't much published anymore about that bug type in general or how you could use it for different targets. In addition to like the releasing the tool and finding these bugs, they also have like a really detailed analysis how exploitable these bugs actually are. And to summarize it in one sentence, if you have a multi-core system, so your virtual machine, or in that case your whole system has multiple cores available, then these double fetch vulnerabilities are trivially exploitable even if the races are really short, so if you don't have enough very much time to switch the value, because just if you have multiple cores you will always win that if you can try often enough. And as the name suggests, like my talk is named Xenpwn, Xenpwn is basically the main inspiration of this research, and I think it was a really great work. So an example of the type of vulnerability discovered with Xenpwn. So this is code from the Windows kernel. It's the NT-app help cache lookup entry function, and you can see the EDI register points to a shared memory location, or it points to user space, which, as for our discussion, is more or less a shared memory location. And they, at offset hex 18, they read like a value out of it and put it into the ECX register. And then they use that as an argument for probe for write. And probe for write basically checks that ECX contains like a valid user space pointer, so a writable user space pointer. So otherwise you could just overwrite like a kernel address, but the probe for write call verifies this is pointing to writable user space. The problem is then they use this address as a destination for memcopy, so they push it as an argument to memcopy on line 9, but they don't use like the already stored value in ECX. Instead, they fetch it a second time from the same memory address. So this is again the double fetch problem. You have like this memory address pointing to user space, and they fetch 2 times, once before the check and once after the check. And if you can just switch the value, then you can bypass the check and have trivial memory corruption vulnerability. And it's interestingly about this code, so we don't have the source code for this because it's the Windows kernel code, but you can't be really sure how this looks like in source code. So is this like a pointer that's dereferenced twice by the user, or is this like a function wrapper, or is this a compiler optimization that makes this double fetch happen? So this is an interesting property of these kind of bugs. So now this was Boxbound. So what's the idea of Xenpwn? And basically the idea is we use the same memory access tracing approach Boxbound uses, but we want to look at paravirtualized device communication. So we are not interested in like user space kernel communication. Instead, we want to break out of a virtual machine. Now the first question everyone asks is, yeah, why you don't simply use Boxbound for that? And the problem with Boxbound is that it's extremely slow. So the Box CPU emulator by itself is very slow. And then if you use the instrumentation they added for Boxbound, it's even more slow by a factor of 5 or something. And you can't it's a passive overhead, so this will affect the whole system. You can't simply do targeted tracing to only look at certain memory accesses. Boxbound will look at all memory accesses and introduce this overhead to the whole system. You also don't have the possibility, so if you install Windows Server 2016 or Server 2012 in Box, it simply won't boot up. So that's of course not a problem of Boxbound, it's a problem of Box, but it still makes this not usable for the research idea I had in mind. And then you have the problem they simply dump these traces into a text file on disk. And they even document that in their paper that this is an approach that doesn't really scale, because if you had really long traces, these text files will grow gigantic and won't be really usable anymore. So my idea was, don't use Box as the CPU emulator, but instead implement this tracing approach on top of hardware-assisted virtualization. And this is the core architecture of Xenpwn. So you have level 0 hypervisor. In my case, this is Xen. That's why it's called Xenpwn. And then you have nested virtualization. So that means you have your target hypervisor and the target virtual machines, and they run nested. So they are in itself are a virtual machine running under Xen. So you have this virtual machine in a virtual machine. And so the boxes in green are basically the communication stuff we want to look at. So these are the shared memory areas we want to intercept. And we have in the level 1 management domain, we have all our tools running. This architecture has the important benefit that you don't have to introduce any modifications to your hypervisor. So I don't write code for the level 0 hypervisor. Instead, all my code, so these are the gray boxes, is the stuff I at least somehow modified or used. They are all user space components that simply run in the management domain for my main hypervisor. And this is just like a Linux system. So all the code I've written is basically Linux user space utilities. This also means if you write shitty code in there, what happens is the user space component crash, but you don't crash all the whole architecture. As I said before, the level 0 hypervisor is Xen, and I'm communicating with Xen using a VMI framework. So VMI stands for Virtual Machine Introspection, and for that I use libVMI, which is basically a hypervisor agnostic library, so you can use that to talk to Xen or KVM, and gives you a really nice C API around all these hypervisor APIs. And this basically allows you to access and manipulate the state of all the guests running under this hypervisor. So you can look at memory state, you can look at the CPU registers, you can even modify them if you want to. And if you use libVMI with Xen, you have access to an even more powerful feature, and it's called memory events. And memory events are basically a way to trap on accesses to a guest physical address. So they are implemented on top of extended page tables. So extended page tables are like the second layer of address translation you can use for hardware-assisted virtualization. And it works like that. So this is like the code I write. So it's just like I register an event for a certain memory address and register like a callback function. So this is just like a pointer to a C function, and it gets called every time a virtual machine accesses this memory address. And it's implemented by like flipping the permissions of this EPT table entry. So the VM isn't allowed to access this certain physical address anymore. If it does so, it raises an EPT violation, which is then handled by libvmi, which calls my callback handler. And using this feature, the idea to do memory access tracing with EMI is quite simple. So we just have to find all shared memory pages. Then we register our memory event handlers. We analyze, so if a memory event is triggered, our callback function will be called, which just analyzes this memory event, extracts all the needed information we need for later analysis, and stores it in a trace storage. And then in the last step, our analysis client can like analysis or do like the analysis algorithm, and that can happen at any later point in time. So it's like an offline analysis. We can just trace for like a month and then do the analysis when we have time to look at the results. So the trace collector is like the core component. It does basically all of these steps besides the analysis. And it's actually the only code I wrote by myself. So it uses libvmi to inspect the memory and to find these shared memory pages. So you have to identify like which memory pages are used by the front end and back end components to talk to each other. And this is part of the code that's target specific. So you have to write that for like Hyper-V and for Xen and KVM because these, of course, they use different data structures and you have to parse them. Then we just register memory event handlers, and every memory event gets like a single callback. And the callback handler does most of the stuff. It disassembles the instructions and looks or stores all the details we want to do. I can see I only have 50 minutes left, so I have to speed up a bit. So the idea is you extract like the domain idea and look. So this is the callback handler. So this is called every time we have like a memory access. And we are only interested in privileged accesses. So we are not interested in bugs in the front end. We only want to look at back end. So we need to check or have a check if this is actually the privileged domain that does the access. If that's the case, we extract instruction pointer, page table values, disassemble the instruction. If we have never seen it before, we use capstone for disassembling, but we only want to disassemble like a unique instructions a single time. So you will see, like you have one instructions that's responsible for like 10 million memory accesses probably. You don't want to disassemble that every time, so we have like this instruction cache. And then we create a trace entry and store that in our trace storage. So this trace storage, as I said, Boxpound simply uses like a flat text file to dump these trace entries. We have some more requirements for that. So we want to have like a fast and persistent storage. It would be cool if it has like efficient compression. So we don't have like gigabytes of data to analyze. And interestingly, there's a tool that kind of fulfills all these requirements, and it's called Xenpwn. And it's not quite well known in like the security industry, but I think it's a really cool tool you can use for a lot of different stuff. So Xenpwn is an open source project by the operating system group at the Karlsruhe Institute of Technology, which is a German university. And the idea is it's designed for full system memory tracing. So it's designed to trace like all memory accesses performed by a system, including the memory contents. And because it wants to support that, it has like a really efficient implementation of all of the stuff. It's a C++ daemon plus a client library. So I use like the client library to interact with this daemon. They communicate over shared memory, funnily enough. But this is like a really efficient way to store these trace entries. And I have a very fancy specialized compression algorithm that's specifically like optimized for memory traces. So this means I have like a compression rate of, I don't know, 99% or something for my traces, because most of the time the information doesn't change that much for like these single trace entries, and it's like heavily optimized for this use case. So I highly recommend it. So what do I store in like these trace storage? And basically I have like a trace entry which is stored for every memory access. It's like the instruction pointer, which means this is the instruction that triggered the memory access. We have the memory address which was accessed. I can optionally store what kind of data was transferred. I don't do this because I don't require it for my double fetch analysis, but this is something you can use for different purposes. And you can store if it was like a memory write or a memory read. In addition, for every unique instruction I see, I basically just dump like the instruction bytes and the module it comes from. So this gives me like a world readable or a human readable way to later look at the instructions and see what action they did. And then the last step is just like the double fetch algorithm. So I just analyze, do I find double fetches? And a double fetch can be, so this is like a really simplified version. It ignores some kind of problems I document in my paper in more detail. But basically you just walk over the trace, so you loop through the trace and look for read accesses to a specific memory address. And if you see in a single context, so in a single invocation of the backend, if you see multiple accesses to the same memory address, then we have a potential double fetch, and then we need to look at that manually. And it turns out this simple algorithm, so this is like, I don't know, 50 lines of C code or something, is actually enough to find a lot of interesting bugs. So advantages of this implementation, basically you have a really low passive overhead because it's just hardware-assisted virtualization. So it's not like the box CPU software emulation or something. It's largely target independent, so you can use this to analyze every hypervisor you want to. You can even use it to analyze like a sandbox or something. You just have to adapt the certain code areas in the trace collector. And it's really easy to write and extend because it's just user space C code. Problem is you have like a really high active overhead. So every time such an EPT violation is traced, you will generate a VM exit. And VM exits are expensive, so this is kind of expensive, and you shouldn't do this if you want to do like full system tracing. But it's okay if you are only interested in memory accesses to like certain areas. The biggest problem I had in practice was that this relies on the support for nested virtualization. Because nested virtualization on Xen, so if you look at the documentation, they basically say, yeah, as of Xen 4.4, this is considered tech preview, so it should work in most cases, but it might be a bit unstable or something. As it turns out, that's not really true. So it works if you virtualize Xen on Xen. It sometimes works if you virtualized KVM under Xen, but one of my main targets I actually wanted to look at is Hyper-V on Xen, and it simply doesn't work. It doesn't get even like to the boot screen. For this reason, all of the results I actually discovered with like the current invocation are for Xen, because Xen on Xen works quite well. Hopefully, or luckily, Server 2016, so the next invocation of Windows Server, actually has support for nested virtualization, so then it should be able to analyze Hyper-V using this toolkit as well. So let's start with the results. What did I actually find? I did tracing run on two different Xen targets. One is in Xen 4.5, one is in Xen 4.4. And the difference is basically because they support different kind of paravirtualized devices. So some more exotic ones, like the SCSI paravirtualized device support, is only included in Xen 4.4. So I just have like these two targeted to analyze all the different devices. It turns out the main problem of doing all this stuff is basically I don't have a way to automatically get good code coverage. It's like it's dynamic analysis, so I only find vulnerabilities if the code executes. Currently I exercise like all this device functionality manually, which is enough to find bugs, but it's probably a good idea to think about how to automatically like exercise all the different functionalities of your paravirtualized devices. In the following, I just talk about like interesting bugs that work with default compiler settings. So Xen released like a really impressive patch for all the stuff I reported, and they patched like a lot of areas in the code that could be vulnerable if compiled with certain compiler settings or optimization levels. I'm just talking about the ones that you actually trigger if you have default compiler settings, because these are the ones that are like useful in the real world. And you can read my full thesis, so I have a link on that that contains a lot of more statistics and stuff about the different results. So the first one, and this is actually one that's not actually exploitable on normal compiler optimizations, but it's quite interesting because it's like QEMU code, so it's the disk backend from QEMU. And you can see, so the source pointer points into a shared memory region. So this is shared memory between between the virtual machine and the QEMU process. And you have this number segments variable, and it's actually fetched like 3 times. So you can see it's like here, and then you have like this if check, and after the if condition they use it. And it's a length variable, so it's a number variable, and you can see if you just look at the stuff in the bottom, you can see n should be larger than number segments, so it's a maximum check, I guess. If that's true, you dereference the pointer again and set n to that value, and then you use it as a loop counter for basically memory write. So if this would be actually translated into 3 different memory fetches, then you have like a trivial heap overflow. And the fun part about this is, so this is like if you have double fetch vulnerabilities in mind, or if you know this bug class, this would be directly looking vulnerable, but nobody has ever like discovered that or talked about that. So it seems to be that the developers didn't really have like this bug class in mind while writing the code. Now, interestingly, it's not vulnerable because, as it turns out, the compiler actually optimizes these 2 memory accesses in a single memory access. So you can't exploit this because between these 2 accesses there isn't a race. My tool still discovered this because there's a third access to this variable up there, and so these invocations are like 2 memory accesses, but this assignment doesn't have any security implications. So it's nothing exploitable, but it's still quite interesting, I think. So exploitable stuff. First of all, there's the Xen blockback code, and this is actually, so this is for for paravirtualized devices that have like, if you use a block device for your virtual machine, which is like the normal use case in enterprise context. So this is the relevant vulnerability. And basically you have like this, so this segments array again points into shared memory, and you have this calculation invoking the last sector and the first sector. So this is the number of sectors you want to read or write to the disk. And they calculate it and put it like here in this variable. And after they calculate it, they access the memory locations a second time and do like a sanity check. So the idea behind this is you should never read more sectors than fit in a single memory page, so in a page size. And if you can bypass this, and you can bypass this by flipping like these values really fast, then you have more or less an out-of-bound read when you are writing to disk, and you out-of-bound write when you are reading from disk. So this is highly suspicious to be exploitable, and I think it's a nice bug. But it's not a bug I want to talk in detail about. I want to go into detail about the Xen PCI-backed vulnerability. And this is my favorite bug of this whole research because it has the interesting property that it's completely hidden from source code. So I'm betting that nobody would discover this bug just by looking at the source code. So basically you have this big switch statement. This is in the PCI backend. Which is a switch statement on this op CMD. And op, again, is a pointer into this shared memory area. And what happens, so this doesn't look vulnerable at all to any kind of bug. It doesn't do much stuff, it's just a switch. But if you look at how this is implemented, you can see the compiler optimizes this into a jump table. So this is a classic compiler optimization to implement switch statements. And a jump table basically, so in this case, in the assembly code, we have this R13 register offset hex 4, that's pointing, or that's equal to this variable. And you can see they compare it to an upper limit of 5, which corresponds to the number of switch cases they have. And if it's larger, they just jump into the default case. But if it's smaller, then the value influences the jump. And the interesting thing about this is if you look into line 4, they fetch this value out of memory a second time before they directly put it into a jump. And now, if you know double fetches, you can see the vulnerability. If we are able to exchange the value between line 1 and line 4, we have an almost direct or indirect instruction pointer control, because we can influence like this goal or this target of this indirect jump. So yeah, that's basically what I just said. So we have a range check, but the range check uses 2 different memory accesses, so we can bypass the range check and jump to more or less an arbitrary location. And it's important, this is like an invalid compiler optimization, so that's not a compiler bug. The bug in the source code is that the variable isn't marked as volatile, so the compiler doesn't expect it to change just without him accessing it. Okay, so actually exploiting this bug. The ways you have available is very small. It's just like these 2 instructions. As it turns out, if you have multiple VM cores, it's really trivial to exploit that. Especially because you can like retry every time you lose. So if you lose the race, this operation will jump into the default case and nothing interesting will happen. But if you win it, you directly get code or like at least the first step to code execution. You can simply do this. So basically, like the core part of my proof of concept is like this assembler loop, which just loops around and XORs the value of opcmd with a value of my choice, so I can flip in between a good value and a bad value really fast. So we have this indirect jump that doesn't give us direct code or RIP control, and so we need to find a reliable offset that we can use to like have a function pointer. The problem is that Xenpwn is normally compiled as a module, so it's a loadable kernel module, so you can't be really sure where it's located in memory. We also don't know what the virtual address of this shared memory backend mapping is, where it is. That's like a random. So in that case, it's quite similar to remote kernel exploit, basically. And the approach I use to get code execution out of this is just to trigger a type confusion, and we use this type confusion to get a right primitive, and from there on we can walk to full code execution. So talking about the type confusion, in Xenpwn there's like a second jump table, and this jump table is stored almost directly behind our jump table we exploit. So the jump table is quickly shown to the left, and the interesting thing is you have like this one state, Xenbus state initialized, that has the following assembly code. So you have the R13 register, it's written into RDE, and then used as the first argument to this Xenpwn attach function. And this normally should be a pointer to Xenpwn device structure, but in our case it's pointing into our shared memory location. So we can like call Xenpwn attach with an arbitrary value of our choice as an argument. When you look at how you exploit this, you can see the first thing the Xenpwn attach function does is basically trying to log a mutex. So there's a def log mutex defined in this structure, and it just calls mutex log on that. So this gives us the possibility to call mutex log on a completely faked mutex structure. When I first saw that, I thought, yeah, a mutex, that's probably just like an integer that gets flipped or something. As it turns out, mutexes under Linux are quite complex, and you have like a fast path that switches like the log count from 1 to 0, but if that fast path fails because like the log count isn't equal to 1, then there's a slow path triggered. And the slow path does a lot of more stuff. And if you look at the code for mutex log slow path, you have several requirements you have to fulfill. So the mutex optimistic spin function needs to fail. That can be achieved by just setting like a pointer to a zeroed page. And if you then have like a log count that's not equal to 1, you have this mutex waiter structure. And the mutex waiter structure is added to a linked list that's pointed to by log wait list. And then after that happens, basically the kernel thread just goes to sleep and wait until it's waked up again. So this waker structure has like a task structure embedded. If the mutex logs fails, the process will go to sleep and just wait for it to be waked up. But simply this addition to the waiter list log list allows us to perform like a somehow arbitrary write, because we control a write of this pointer to this waiter structure to a location of our choice. So this is a write where, so we can arbitrarily choose where to write, but it's not a write what. So we can't directly control the value that's written, otherwise it would be too easy. Instead, what we write is a pointer to an attacker-controlled function. So we can't simply override function pointers, making this exploit a bit harder. And the biggest problem in the exploit is it's a one-shot exploit. So you can only trigger this write once, because then this whole PCI back function is basically locked up, because this original function we abuse is never returning, and then you have like a state lock and can't trigger multiple memory writes. So the core idea is we just want to add faked entries to the global linked list. So we have like, if you look at like how linked list is defined, and we have this pointer to attacker controlled data, it basically allows us to add a fake entry to a certain linked list. And that's what we want to use to exploit this. So this is how, for some arbitrary linked list, this looks like before. So we have like this list, this linked list, and this is like the way it's implemented in Linux. You have like a double linked list with next pointers and previous pointers, and we have like our fake mutex stuff, and this one has like a previous value pointing to this list head. And after we trigger our write, we have the following like a memory layout. We still have like this list head, and it points to this waiter structure, which is stored on stack, and we don't control that. So this is basically junk we don't really control. But the next pointer of this waiter structure points into controlled data from us. So we have a couple of requirements for this linked list. It has to be a global data structure, because then we can be sure, so for a certain kernel version it will always be at the same address. Because we need to know the address of list head. So the requirement for this exploit is basically knowing the kernel version of the host system or the management domain, which might be a problem or might not be a problem depending on the exact environment. There shouldn't be like new elements attached to it during runtime, because that will like use the previous pointer and stuff like that, and will delete our entries basically. And the function, and that's the most important part, the function that uses this linked list needs to survive one junk entry. So basically we can't control the stuff shown here in red. So if a function that iterates over this global list just crashes when it sees this waiter function or this waiter data structure, then we don't get anything interesting, because it will never use our controlled data. So I started looking into global linked list and what stuff there might be. And interestingly, so that's actually code from the 90s. It's in the exec implementation from Linux. So you can see it has like the copyright of Linus Torvalds from 1992. And there don't seem to be a lot of changes in this code since then. And basically this file defines a static list or a global data structure called formats. And formats contains a linked list to all the different file formats that are supported by exec. So if you do an exec, this linked list is walked to check, if it's an Elf file or a shell script, or even like this a.out format nobody uses anymore. And if you look at the code, it basically calls the try module get function. If that succeeds, after that, it will call the load binary function, and this is a function pointer that's under our control when we are like in our entry. Luckily, this waiter entry that's not in our control will be skipped, because the try module get function fails for this entry. So it's not a valid module here. So this one fails. We go to continue, come to the entry we control, and then we can like have an arbitrary function call. And from that on, it's quite easy to exploit this. So we set this load binary pointer to a stack pivot, so we do kernel rob. We then have a rob chain that allocates executable memory and copies the shellcode into that executable memory. So we just use like VM allocs and memcopy. So the rob chain is actually quite complex, but because you are in the Linux kernel, you have like infinite rob gadgets. So it's kind of a nice exercise to do. Then we restore like the original formats list. Otherwise, everything would be crashing because nobody would be able to exec new programs. We have like our $shellcode that just pops up a shell or does whatever kind of advanced stuff you want to do. And then we quickly return to user space and we just let the process who does the original exec, it will die a horrible death, so we just like dump it. But instead of that, our shellcode will have hopefully done something cool. Yeah, and I have a demo for that, so I hope it will work. And I think I'm heavily over time, so I have to hurry up a bit. So basically, you can see I have like two shell windows. Both are, yeah, that also works. Both are on the guest system. And the idea is I want to get like a shell on the host system. So what I'm doing right now is the exploit is like split it into two parts. So this is actually the race condition part. So I have this override function binary which tries to override this opcmd value. And it will only work if I actually trigger some kind of activity on the PCI device. And I can do that manually. If I use this lpci command, you can see I have this one paravirtualized PCI device, and I can run this a couple of times, and you see I get the same output. But what happens if I do this in parallel? So I have like on the left-hand side, I have this override pointer function, and you can see the lspci function hangs, and that basically shows I have won the race even in the first try right now, and have overwritten this formats pointer. So I just wait until the lspci program finally times out, because then it will not mess anymore with my shared memory pages, and then I can start the second part of the exploit. So the timing out takes. Yeah, now it's timed out. So and now I'm just like opening up a shell. So my payload is just a simple reverse connection payload. You can probably do something more advanced. And I do the prepare shellcode code, which actually triggers like, so this puts like the right values into every location. So this whole exploit I just described will work. And if I now oh, that's great. It didn't work. So if I now just like execute a comment on the shell, but you can see it rebooted, so I have to restore from the snapshot and try it again. That's the demo gods. If Georg's demos doesn't work, mine don't work, of course, as well. But it's actually in theory, it's quite stable, so it should work most of the time. So I just set it up again. So now again, we see the hang, so we triggered the override. We wait for the timeout. So the timeout happens because it still tries to communicate using this to this PCI device, but the PCI device is locked, so we have to wait a bit, but now it worked. And now let me just do it again. We have this netcat. And we do this prepare shellcode. And it crashed again. I do the demo while WhiskeyCon. That's probably... I'm already over time. Sorry for that. I was really sure it should work. Okay. Yeah. Sorry about that. Final slides, you can find my thesis describing Xenpwn in greater detail. You can find this online, so it has like everything besides the exploit. And the exploit and the white paper will be released after Infiltrate. I also plan to release Xenpwn as an open source tool, and my 2016, I just have to like fix it up so it works on other systems than my own. And next goals are basically I want to use Xenpwn against Hyper-V and VMware, which requires like improved support for nested virtualization. I want to identify and analyze other shared memory trust boundaries, so mainly sandboxes. And an open question is what types of bugs can we find with full memory traces? So currently we trace without memory content, so it would be quite interesting. If we trace memory content, can we find different type of bugs besides double fetches? So thanks for your attention. Sorry I fucked up the demo, and if you have any questions, just feel free to ask.
Question? Thank you. Anyone? Anyone with questions? No? All right, Felix, thank you very much.
Thank you.
Thank you, Felix.